Hello again. We are going to do some more problems using trigonometric identities. First of all, let's prove this trigonometric identity. As you see, the left-hand side is a complicated expression. It says 1 minus 2 sine squared of x over cos x plus sine x, and then plus 2 times sine of half angle, which is x over 2, cos of x over 2, equals cos of x on the right-hand side. So I don't think anybody would start with the right side, proving that the right side is equal to the complicated expression on the left-hand side. So logically speaking, every person would start simplifying their left-hand side and trying to reach the right side of this identity. So I'm going to be logical too. So I'm going to copy the left-hand side first of all. So cos x plus sine x plus 2 times sine of half angle cosine of half angle. Now 1 minus 2 sine squared in the numerator, if you think about it, it's an identity that we have had before. So you have to actually master all these standard trigonometric identities. 1 minus 2 sine squared of x is actually cosine squared of x minus sine squared of x because it is equal to cos of 2x. And cos of 2x itself is equal to cos squared of x minus sine squared of x. So these are all equivalent identities. So instead of 1 minus 2 sine squared of x, we can write cos squared of x minus sine squared of x. And if this is not a good explanation, which of course it is, I can explain it in a different way. I can say instead of 1, we may write actually sine squared of x plus cos squared of x. That's the most fundamental trigonometric identity. We know that sine squared of any angle plus cos squared of the same angle is always equal to 1. So that is 1 minus 2 sine squared of x all over cos x plus sine x plus, now the other part, I think we can use the double angle formula for sine, I believe, because sine of double angle is 2 times sine of angle, cosine of the angle. So here our angle is x over 2, so obviously double x over 2 would be just x. So this whole combination in reality is sine of x. So now sine squared minus 2 sine squared is going to be just negative 1 sine squared of x. So we end up with cos squared of x minus sine squared of x over cos x plus sine x, and then plus sine x. So in the numerator, we can factor the expression actually, because this reminds me of the famous identity in algebra. It was called difference of squares. I don't know if you remember it or not. A squared minus b squared was equal to a minus b times a plus b. So here what plays the role of a is cos x, and what plays the role of b is actually sine x. So we do have a squared minus b squared, which is a minus b times a plus b. So the numerator can be factored as cos x minus sine x, and then times cos x plus sine x, okay? And in the denominator, we have cos x plus sine x. Now, you see that when we factor the numerator, we end up with a factor of cos x plus sine x, which is exactly the same factor we have in the denominator. So these two are cancelled out because the ratio is equal to 1, whether you like it or not. So the only thing that is left after we simplify is just the first expression, cos x minus sine x. So cos x minus sine x plus another sine x. Of course, sine x and minus sine x, they're opposite expressions, cancel out each other, and we are left with cos x, which is exactly the right-hand side we wanted to reach. So we proved this trigonometric identity using the other known identities that we have studied in the past. Other types of questions, not necessarily these types. I've done these kind of questions in the past a lot, but not necessarily these types that you prove trig identities. Here it says we have a sine of 2x plus b cos 2x plus c, and a, b, c are just real numbers. And this is equal to 2 cos squared of x plus 4 sine x cos x. The question says find the values of a, b, c. So a, b, c are real numbers, and we're supposed to find a, b, c such that left side is equal to right side. So In order to do this, perhaps what we can do is to use trig identities again. So instead of sine 2x, I can write 2 sine x cos x. And instead of cos of 2x, I can write right here. It says 2 cos squared of x minus 1, and then plus c. Okay? And the other side, we have 2 cos squared of x plus 4 sine x cos x. Let's see if we can simplify anything here. I think we have 2a and then times sine x cos x. And here we have 2b cos squared of x. And then we have minus b plus c equals 2 cos squared of x plus 4 sine x cos x. Now, if you look carefully, you will notice that the product of sine x cos x is repeated on both sides. And cosine squared of x is also repeated on both sides. So what we're going to say here, we're going to say in order for this equality to hold, the coefficients of cos squared of x on either side and the coefficients of the product of sine x cos x on either side should be equal to one another. So that means that this 2a here and then that 4, these two should equal to each other. So 2a must be equal to 4. And the coefficient of cos squared of x is 2b. So that 2b and this 2, these two must also match. So 2b must equal to 2. Okay. And I believe there is nothing else left here. On the right-hand side, we don't have any constant, so we have plus 0 in reality. But that 0 should be equivalent to the leftover constants from the left-hand side of this equation. So this means that negative b plus c should equal to 0 because an obvious reason, there is no constant term on the other side. And we already said that 2a should equal to 4. We already said that 2b should equal to 2. So we end up with 3 equations and 3 unknowns. From the last one, I can say b is equal to 1 clearly. If 2a is 4, then that means that a is equal to 2 because 2 times 2 is 4. And if that's the case, from here we can say c is equal to b. But b was 1, therefore c is also equal to 1. So the question was asking us to find the values of a, b, c such that the left expression equal to right expression. And we see that if a is 2 and b is 1 and c is 1, then left side will equal to right side. In fact, why not? We can even write this down. We can say 2 times sine of 2x plus 1 time cosine of 2x plus c, which is 1. This is the expression on the left-hand side. This is equal to 2 cos squared of x plus 4 sine x cos x. So this becomes actually another identity, which actually you can sit down and prove it. So another question here, it says if cos of x is 3 over 5 and angle x is between 0 and pi over 2, which means that the angle is an acute angle in the first quadrant, it says find the values of the rest of these expressions, sine of 2x. So sine of 2x, we already know the formula, don't we? It is 2 sine x cos x, right? Cos x is 3 over 5, piece of cake. You can just substitute that, okay? But the thing is that we don't know what sine of x is. So we need to find sine of x. But how do you find sine of x given the cos x? Well, you can use trig identities again. So this exercise, you see that it's not a proving trig identity, but you are actually using trig identities to solve it. So we're going to say cosine squared of x is 1 minus sine squared of x. Therefore, cos x would be square root of 1 minus sine squared of x. Now, some of you are thinking why I did not write plus minus, because generally when you take the square root of both sides of an equation, you write plus minus. The reason why I didn't write the minus part, because I knew that both sides are positive. Why? Because angle x is an acute angle, and when you're in the first quadrant, when an angle in standard position is in the first quadrant, sine, cos, tan, all of them are positive. Okay, so the negative is like out of question, and that's why I didn't write that. So Now I'm going to say, actually, I have to use the other one because I have cosine. I want to find sine. So I'm going to write the other identity. So I'm going to write sine x equals square root of 1 minus cosine square root of x. We can find one in terms of the other. So that's 1 minus 3 over 5 all squared, which is 9 over 25. So this, after you simplify, you get 16 over 25 under the radical sign, which will give you 4 over 5. So sine of x equals 4 over 5 if cos x is 3 over 5 as it is given. So now that we find the value of sine x, so we can substitute 4 over 5, and the rest is piece of cake. You just multiply. It's going to be 2 times 4 is 8, 3 times 8 is 24 over 25, and that is the answer for sine of 2x. For cos of 2x, we can write 2 cos squared of x minus 1. That is the double angle formula for cosine. And because cosine is given, so that's 3 over 5 squared minus 1. That would be 9 times 2 is 18 over 25 minus 1. And 18 minus 25 over 25, that would be negative 7 over 25. And it makes sense to tell you the truth. I'll tell you why, because the angle x is acute, okay? So double x, like 2 times x, would be an obtuse angle. Or apparently it is an obtuse angle. And if it is, so its cosine must be negative. Now, we could have ended up with a positive answer if we didn't have 3 over 5. If it was some other number, maybe we would end up with a positive value. And in that case, we would say, well, both x and 2x are acute angles, like 12 degrees and 24 degrees, instead of 70 degrees and 140 degrees. So when the angle is 70 degrees in the first quadrant, double that angle could be 140 degrees. But if it is like 12 degrees, double that angle could be 24 degrees, which is still in the first quadrant. So we don't know. We have to see what the numbers are giving us. In fact, now that we have access to a calculator, if I find inverse cosine of 3 over 5, it gives me an angle which is 53 degrees. Okay, so 53 degrees. And if you double 53 degrees, that will be 106 degrees, which is an obtuse angle. So we see that it makes sense that the cosine has become a negative answer, because in the second quadrant, cosine is negative according to the cast rule. Tangent is the ratio of sine over cos. So it's needless to even talk about this. It's so easy. So 24 over 25, all divided by negative 7 over 25 will be negative 24 over 7, which is the value of tangent of 2x. So given cos x equals 3 over 5, and given the fact that the angle is acute in the first quadrant, we did find the values of sine 2x, cos 2x, and tangent of 2x in this exercise. We didn't prove any trig identity here. In this question, we did prove, and in this one, we didn't prove, but we found the values of A, B, C such that the equality would become an identity. Thank you for your attention.